Hey guys, welcome to Unit 7, Section 2, the Pythagorean Theorem, Converse. Okay, so this lesson definitely still deals with the Pythagorean Theorem, but we're going to be looking at a different way to utilize it because we're going to use it for triangles that aren't just right triangles. But to start out, we're going to go ahead and think about, in order to be a right triangle, it has to fit perfectly into the Pythagorean Theorem. So if we want to think of this as the reverse, we can actually use this theorem to test if something's a right triangle. So in part A here, we want to identify the fact that 6 and 9 are smaller than the square root of 117. That's going to be like 10.8 or 10.9, something like that. So what we're going to do is we're going to say this is our A, this is our B, and this is our C. So we're going to get 9 squared plus 6 squared equals square root of 117 squared. 9 squared is 81, 6 squared is 36, and when you square a square root, basically it just undoes itself and you get the number inside. 81 plus 36 does end up being 117. So since these sides are equivalent, this is true, therefore making it a right triangle. So this is going to be a yes. Now let's test it with these ones. So since they're already lined up for us, we're just going to go A, B, C. The last one has to be C because it's the biggest value. So we're going to get 6.1 squared plus 9.4 squared equals 11.3 squared. Now what you're going to want to do, I'm just going to split screen with my calculator just to save some time. All right, so 6.1 squared is 37.21. And then we got 9.4 squared, which is 88.36. And then we have 11.3 squared, which is 127.69. And then we got to add these and see if they're equal to each other. So I'm going to add the 37.21 plus 88.36, and I get 125.57. Then I look and see and notice this is not the same. So since those are not equivalent, this is not actually going to be a right triangle. If it was truly a right triangle, those values would have fit into the Pythagorean theorem. Now, we can actually use this in a different way too, because if it's not a right triangle, then it has to be either an acute triangle or an obtuse triangle. So the idea is, with an acute triangle, we're still comparing c squared to a squared and b squared, but if it's going to be acute, then it's going to be less than the other two sides combined. Okay, and then the other side, c is going to be greater than a squared plus b squared. The reason that it happens to be this way is because when the two small sides end up, their squares are bigger than the hypotenuse, it shrinks that angle so it's a little bit smaller. And then the last one, when it's an obtuse triangle, c is larger than the other two combined, so it increases the size of the angle across from it. And this comes from the hinge theorem. The bigger the angle, the bigger the side across from it, and that's the idea. Okay, so now what we're going to do is classify each triangle below as either acute, right, or obtuse. And then, yeah, we're just going to start there. All right, so this first one, we have 21, 16, 24. We don't know if it's going to be a right triangle or not. How I would suggest labeling these is just go from smallest to largest, A, B, C. So it's going to be 16 squared plus 21 squared. And you can just write equals because we don't know if it's going to equal. We're just going to start with that because that's what we're used to. We can always change our sign afterwards. So 16 squared is going to be, I'm going to again split screen, 256, 21 squared is, I don't know that one off the top of my head, 441. And then 24 squared is 576. So when we add these two small sides, the 256 plus 441, we get 697. Since the two sides are actually bigger than our hypotenuse squared, we go back up and we think about which situation this is from our list of three. Since it didn't equal, it's not a right triangle. And since A and B together are bigger than the C, which is what happened for this one, this is going to be acute. All right, let's try the next one. So again, going smallest to largest, we're just going to say A, B, C. So we're going to get 5 squared plus 7 squared equals 9 squared. 5 squared is 25, 7 squared is 49, and 9 squared is 81. 25 plus 49 gives us 74. This time, this is A, B, C. C is actually going to be the bigger side, so we're going to change this sign because they're not equal. We're going to make that this sign. So since the C is the bigger part, it's going to be obtuse for number 2. All right, so that's how you apply those theorems. And then this one is just more application with the Pythagorean theorem. We're not going to worry about these for right now. Just focus on utilizing this and then doing the homework related to the converse of the Pythagorean theorem, which is Unit 7, Section